Hello, everyone. Glad you're here. We're going to talk about geothermal for high-rise buildings and the design considerations of them. My name's John Rath, and my job today is to get out of the way, get in the back of the room, get the microphone to you when you have questions, and make sure that if you are looking for CEU credits, that I get your signature on one form or another in the back of the room before you leave. Even if you registered at the NY-GEO website for the credits, I still need a signature. That's a New York State Society of Professional Engineer requirement. So please do that. I would like to just introduce the moderator for today's panel. He's a gentleman that I get to work with and my boss Christine gets to work with on a regular basis. He's a member of the Edison company, Colin, Rojas, and the department he is working for, which I think is fantastic, is the geothermal department or the clean heat department for Edison. I'm hoping every utility company will match them and get the same kind of department so we can work with them. Please welcome Colin.
Thank you, John. So my name is Colin Rojas, and I'm the program manager for Edison's commercial and multifamily geothermal program. A few items about the program before we get into the panel. We provide Con Ed customers with rebates when they install geothermal heat pump systems, and we recently just released a thermal conductivity testing incentive for customers to engage with as well. Our rebates have supported the installation of geothermal heat pumps at many of the projects talked about yesterday and today: 1 Java Street, 555 Greenwich, 1515 Surf, St. John's new Health Sciences Center, the Alafia redevelopment, and the Marcus Garvey extension, among many more which are currently breaking ground. I promise that's the only self-promotion I'll be doing on this panel. Today, we're lucky to be joined by 3 panelists that have all been involved in the deployment of geothermal heat pumps across New York City and the surrounding area. We have Brian Urlaub from Salas O'Brien, Jason Eitel from EJS New York, and Sam Gerber from CDM Smith. I'll give each panelist a couple minutes to introduce themselves and their firm before we hop into our discussion.
Hey, so good afternoon, everybody, or morning, everybody. Oh, man, bad start. So my name's Sam Gerber, work with CDM Smith. You know, we've done a ton of geothermal work around the city and getting into U10s as of late. So if you went on the tours, 1515 Surf, 1 Java, do a ton of ground design, ton of geothermal work. Very excited to see where it all goes.
Good morning. Wow, that's loud. I'm Jason Eitel, a partner of EJS New York. We're a manufacturer's rep of HVAC equipment in New York City, surrounding areas. We are talking today, or I'm specifically talking today about the heat pumps in the rooms, in the apartments. There's a lot of really interesting technology that we've learned throughout this conference, and a lot of it is relatively new to me and my team, that you have this network of piping and you're exchanging heat with the ground. Well, on the unit level, at the apartment level, where we get cooling and heating, it's relatively commoditized, because by that time that warm water hits the building, now we got to get cooling in the spaces. So what I'm going to kind of get into today is about how we're utilizing that warmer water and how we're utilizing the ground to reject that heat at the apartment level.
Thanks, Jason. Yeah, good morning. My name's Brian Urlaub. I'm with Salas O'Brien. I'm the Director of Geothermal Operations with Salas, so I'm involved in almost all of our geothermal projects across North America. I've been in the geothermal industry for over 25 years. I took my first international ground source heat pump class in 1998, so it dates me a little bit. But anyway, yeah, here to talk about tall buildings. How many designers do we have in the room, engineers? Quite a few, okay. This is a bigger crowd than I expected for this topic, so this is great. So yeah, we're just going to kind of talk about, what are things to consider and, some nuances about tall buildings with geothermal. So thanks for coming. All right, I'm first. Let's see if this works here. Okay, couple of learning objectives. This is a PDH course, so we have to put this in here so you can get your credits. But obviously there's some specific challenges with tall buildings related to geothermal, number one, but obviously just in general, when you start to get over around 30 stories, things tend to change between stack effects, piping pressure, and then of course generally you're in a very small footprint related to the square footage of the building. So if you're going to look at geothermal and other technologies, how does that play into the land area, how much available area you have for geothermal underneath the building, what other assets you might have for thermal resources. So we're going to look at all that. We're going to talk a little bit about the thermal load profile, because obviously that's the foundation for all design, is really understanding what does that thermal profile look like throughout the year, and then long term, obviously, when we're talking about geothermal, how it impacts the ground and the bore field. So really understanding that when you start to get tall buildings, it's amazing. Even in New York City, you flip from a heating dominant application to generally a cooling dominant application, which is extremely important when related to geothermal, right? Because with the limited ground area, if we're putting a lot of heat in the ground, how does that impact the ground over the long term? And so we've got to look at that. And then of course ventilation. We're going to talk about that a little bit. Ventilation is a really big part of tall buildings. Obviously you're going to have multiple mechanical rooms across the height of the building. So you might have a couple of mid floors with mechanical, and then the roof. Is the ventilation going to all be related to or connected to a geothermal system? Will some of it not be on? You can actually split it between heating and cooling to really try to help balance the load. So looking at how that works in relation to the building itself, and then of course the geothermal system. And again, with tall buildings, you have very small roof area, and you have very small footprint to deal with all of your equipment and your thermal assets. So kind of what, some steps within the design process, especially early on. Obviously I mentioned first and foremost is that thermal load profile, really understanding the dynamics of the building. How much glass do you have? Generally you have a lot of glass in tall buildings. So again, we're flipping to probably a cooling dominant application. And so really understanding that. And then of course your solar gains from morning to evening, and how that changes within the building, how much diversity you have within the building. All those things really become important and critical to designing a geothermal system. So you can understand how to leverage that diversity versus just a traditional system where you're just turning on a boiler or a cooling tower. Maybe we're also incorporating some other technologies or other parts of the building systems like domestic hot water. So really adding all that into your thermal load and really getting a fine tooth, or a fine or granular thermal load profile is really important. Understanding the facade, how efficient the envelope is going to be, and then of course that ventilation is all part of that. So. And then looking at your thermal assets, what are you going to have? Generally, a tall building, you've got a lot of units, right? So you're going to have a lot of occupancy. You should have a lot of wastewater. Is that an asset? Potentially. Geothermal underneath the building, that's obviously an asset. Is there piles? Can we use energy piles? That could be another asset. Maybe there's some air source opportunity to help hybridize the system if you can't do it all with one technology. So just understanding what are all the thermal assets that are on site that could potentially be used to handle the entire load of the building, okay, and completely electrify it, because that's our goal, right? Be 100% electric, using very efficient technologies to get there, so we're not increasing demand on the grid. But so going through that kind of process early on and understanding what all those look like is important. And then, of course, looking at, there's a lot of different ways to pipe up a system schematically within a tall building. Most of what we're talking about today is a traditional heat pump in unit application. Every now and again with some tall buildings, I'll just mention that there is, especially talking about high-end condo market or high-end market rate markets, they may end up doing fan coils with 4-pipe systems because of keeping all the compressor and main components into a mechanical room versus in suite. But most of the time you're looking at in-suite heat pumps, which is, yeah, what Jason's going to talk about. So, and then of course the heat pump technology, which again he'll get into. So again, we got limited roof space, you know, and that goes to putting all your boilers up there if it's traditional, your cooling towers, you know, all that stuff that goes on the roof. If we can eliminate some of that stuff, then maybe we had opportunity to increase the amenity space up there, which developers love because that's the highest rentable square foot in a building is the upper floors, right? Those are the most expensive. And then if you have rooftop amenities, it just increases value. So if we can eliminate some of that stuff by using geothermal, that really does actually help this become a more marketable property, okay? But how do we do that? Well, we've got to use geothermal. We've got to use some other technologies to open up that roof space. But we're going to be limited. So because of the footprint and, again, the building size, you have to understand that and see what you really have for available space, okay? And then, again, available land. You know, these are generally on postage stamps, and if you have a 50, 60-story building, you know, that's a lot of square foot to heat and cool with a very limited ground area. So when we're talking about geothermal, what are we going to put in the ground to try to maximize the thermal asset and provide as much capacity we can for that building? There's a lot of technologies we can look at, okay? There's a lot of heat exchanger technologies. There's energy piles. You know, there's deeper drilling today than we've ever drilled, you know, in the past. It used to be, especially in New York, you were, you know, capped at 500 feet. Now we're drilling to 800 feet. There's obviously standing columns and other projects that are down to 1,500 feet. So you really have to look at geology, cost to drill, how much space do I have, what's the foundation comprised of, can I utilize the foundation, do I have to coordinate around it, is there subgrade parking? You know, in New York, you also have to understand what's beneath the site, MTA, you know, aquifers, you know, your water tunnels. There's all kinds of stuff under the ground. So just understanding that's really important. But you have to look at all your technologies and figure out what's the best, you know, for the application. But the nice thing is we have options. We can maximize the geothermal heat exchanger capacity by using maybe some different technologies, and that's continuing to evolve. We're seeing a lot of that technology, you know, in both drilling and heat exchangers coming into the market, which is great. It helps us get to where we want to go. Again, window to wall ratio, I mentioned this. Generally, you're getting a lot more windows than walls. So understanding how that impacts your thermal profile and then your comfort within the building, okay? Obviously, we're in New York. This is a, you know, a heating dominant climate zone, so we need to understand that. What's the comfort going to be like in the building because of that? Your electrical capacity, you know, we're electrifying these buildings. This is all going to change from your traditional systems, right? So we've got more electrical capacity that's required for these buildings. You do get the stack effect. So, you know, with tall buildings, this is definitely an important thing to consider when you're looking at designing these buildings, okay? Especially in your corridors, elevator shafts, et cetera. You've got to look at all the stack effect, and that really does come into play. So again, we mentioned the potential heating sources. There's a lot of different opportunities here. We mentioned wastewater. Obviously, electric resistance is really not a good idea. But we do have some air source opportunities now. Manufacturers are really starting to develop large tonnage air-to-water heat pumps that can help with either domestic water and or supplement the geothermal system as a hybrid. So we've got a lot of opportunity. We've also, you know, thermal storage. And there's some great PV and solar systems out there that you can put on the facade. There's, you know, the different electronic shading like view glass that you can really impact the cooling load from the glass perspective to help with electronic shading. So there's a lot of different technologies that can really help that load profile become balanced, which is what Sam's going to talk about at the end, because that's extremely important for long-term, you know, with the geothermal system, the long-term net effects of the bore field. So again, and just, you know, the operating cost savings versus, you know, different technologies. This is just a little graph kind of showing that obviously water source heat pumps connected to geothermal are going to be your most efficient, but you may not be able to utilize that technology to 100% of the capacity just because of the type of building it is. So you're going to have to look at other technologies. And again, we mentioned comfort, the stack effect, all the glass, you know, looking at how do we design the interior spaces with heat pumps, understanding that heat pumps generally have much lower supply air temperatures than traditional systems because of the temperature profile that they operate under. So understanding that and making sure that you still have comfort within the space is really important, okay? So those are just some considerations that you really have to look at. Then, of course, if you're using fan coils, with low temperature hot water, again, lower supply air temperatures, making sure that we don't have any uncomfortable situations with all the glass in the space on the perimeter. All right. Again, we talked about all types of heating here. For tall buildings, VRF's probably not really much of a choice. I mean, it's just too much mechanical space that you would be required to run all your refrigerant lines, put all your condensing units. So it's generally either in-suite heat pumps or fan coils, okay? And then domestic hot water. Domestic hot water on these tall buildings is really important because it can be a great thermal resource now that we've got a cooling dominant load profile is for all year to pull some of that heat off of the system, reuse it as waste energy to heat your domestic hot water. And that can help balance your bore field for the long term. You've got a lot of simultaneous heating and cooling going on, so your efficiencies obviously increase dramatically for domestic hot water, okay? So that's all a really great technology now and there's a lot of heat pump technology in that space that's become more available for, reaching the 130 to 140 degree temperatures, working off of geothermal sources, with different refrigerants. So that's a really great technology to also incorporate into the design and really help try to balance that profile and bore field energy for the long term. And, we mentioned this, there's obviously some central air to water systems that can be incorporated into domestic use, but that would have to take up, some roof space. So one thing that you're gonna have to keep in mind, if you're gonna use wastewater as a thermal asset, where does all your wastewater exit the building? At the bottom. Generally in high-rise buildings, all your domestic hot water plant equipment is on the roof. So now if I'm going to put any heat into my domestic hot water, I may have to completely reverse my domestic hot water piping from being fed from the top to the bottom. And how does that impact pumps, pressure, a lot of different things. So if you're going to incorporate some of those technologies, it may completely change your design on where you're going to put equipment and then how you pipe the building and what you would normally do. So you got to know that stuff pretty early on, okay? Sometimes they do unitary hot water, not generally on larger buildings, but sometimes they do, which, certainly could be the case. Most of the time that's going to be electric. If you have heat pumps in the suite, depending on the style of heat pump, maybe you could do some type of a hot water assist off of the heat pump system. If it's a vertical stack, probably not. But if it's an actual packaged water to air heat pump, there's a possibility there. So it just depends. And again, ventilation's also, one of those things you really have to look at. Is it, obviously you got to do corridor ventilation. They usually pressurize corridors. So that way people are cooking, the smells aren't out into the hallway. So you pressurize everything, but then your in-suite heat pumps, and I know Jason's going to talk about too, maybe having an incorporated ERV in your vertical stacks or your heat pumps in the suite. So you got to look at all your ventilation and how you're kind of handling that. But certainly energy recovery is a big part of it. You need to reduce, the energy overall. But then again, how does that change your thermal profile of the total in looking at geothermal specifically? Because we need to understand that if you're going to size a ground loop that's going underneath the building and going to be there for the next 80 years, right? So again, a lot of different ways to get the ventilation to the spaces. I mentioned ERVs is important. Obviously, you can still do some natural ventilation, but harder to meet some of the codes with natural ventilation. All right. Yeah, and this is just kind of some examples of some thermal profiles, without energy conservation measures, doing some variable flow ventilation. You can see the reduction, in the load profile, how things kind of change. Not as much heating requirements, but still a lot of cooling. I think Sam's going to touch on that quite a bit, on how that really changes between heating and cooling, okay? And of course, envelope improvements. Envelope is very important. We're seeing some passive house designs, not in necessarily tall buildings, but medium-rise buildings in New York. And it's amazing how much cooling you need and not enough, and you don't hardly need any heating. I mean, it's crazy how that really flips everything on its head when it comes to your thermal profile. So envelope is extremely important in how they're going to build the building. And these are just kind of some energy savings with some different, options, obviously. for ventilation and envelope. So, with that, I think we'll turn it over to Sam. Jason. Or Jason's next, sorry.
Good afternoon, everyone. Thank you for that. That was really cool to learn. Like I was saying at the beginning, you know, we've from an HVAC perspective at the equipment level, you know, we've had an evolution of product in the apartments since I've been doing this for about 20 years. And heat pumps, for me, have literally built a career. There's a lot of heat pumps in New York City. And it really hasn't necessarily been an effect of geothermal, right? And I went to RPI. I'm a mechanical engineer. We learned a lot about geothermal systems and how to apply heat transfer and thermodynamics. And everybody said, wow, the geothermal thing really makes sense. Oh, but you're going to New York City. So New York City, we don't do geothermal in New York City. It's never really a thing. All right, NY-GEO, I met Zach Fink. Zach Fink has kind of changed that whole mindset, at least in my mind, in my company's mind. And so heat pumps, as much as heat pumps has been a big part of our company, and I think of this city, now it has even a more overwhelming effect because of the systems that we're using them in. So talking about a little bit like how this presentation is more or less tailored towards specifying engineers and product benefits, features, that sort of thing. But if you think about the evolution of product from when 20 years ago it was a PTAC system, right? We had PTACs in the apartments below the windows. When I started at the train company 20 years, we were selling PTACs, right? PTACs, blowing the curtains around, packaged DX, air-cooled through the wall, water dripping off the sleeves, hitting people in the head. That was what people used in their apartments for heating and cooling. Then they had a hydronic heating loop that went throughout the building because New York City naturally has district steam, right? So they would take that heat from the steam through a heat exchanger and they'd run it through a hot water coil on the PTACs. So there'd be this really hot water coil, really hot water coil, 180-degree water on top of the PTAC. And over years, those things would just break down, right? And so bad in-suite experience, they're noisy, you hear the outside. New York City is a loud place, you could hear it through the wall. So there was a need for something in the apartments. So everybody said, all right, well, what if we got rid of, we still have 2 pipes with a PTAC system. What if I had 2 pipes with a condenser water system? Let's do water source heat pumps. Okay, so water source heat pumps, and most manufacturers had a horizontal heat pump. And the heat pumps, they went in the ceiling. Right? Well, in the heat pump in the ceiling, you have compressors, and you have a couple heat exchangers, and you have fans, and you have control boards. And then the architects gave us like a 10 by 10 axis panel to service that unit. And it became a disaster. People tearing down ceilings because I have a bad filter. I can't even get to the filters anymore. So access became a big thing. So those became a problem, and people were like, well, heat pumps make sense, but I can't access them, and it makes the in-suite experience that much more difficult from a service perspective, from a living, from a maintenance perspective. So the vertical stacked came about right around 2004, 5, 6, only a couple manufacturers building vertical stack heat pumps. And a vertical stack heat pump is exactly that. It's a vertical heat pump that we align in a stacking arrangement up the building, right? So in these high-rise buildings with typical templates of rooms with respect to the kitchen and the exterior walls and the columns, it's pretty much a stacking arrangement. That's why we call it a vertical stack heat pump. And these heat pumps run slab to slab. And so the manufacturer we're going to talk about today makes a vertical stack heat pump that will build that heat pump custom to slab. And we talked about the lower leaving air, or the lower heating leaving air temperatures than your typical fan coil system. We can raise that discharge closer to the ceiling so that you get better distribution of that air from a heating perspective, better wash on your windows. So we are, as a manufacturer's rep, have multiple heat pump products in our portfolio. Enertech is one of our manufacturers. We have Jetson air-to-water heat pumps on the roof, air source heat pumps, making hot water for domestic and injection purposes. And Omega is the product we're talking about today. So Omega was established in 1997. It's a Sigma heating and cooling company. They also have a wet heat product. Sigma is one of their more well-known brands of wet heat in the city, right? A lot of these projects, high-end projects, you have some sort of baseboard along the windows. Sigma does those. They have a self-contained product that can do up to 25 tons, air-cooled and water-cooled. They also make a vertical stack fan coil, right? So from a perspective of vertical stack arrangement, you can do the same thing without a compressor, and it's a fan coil with cold water and hot water. Again, 2 pipes. Everybody's trying to save money, so 2 pipes throughout the building, and now you add the geothermal portion to it, you get that incentive from a tax credit, but you also get the incentive of exchanging heat from one side of the building to the other. So we have a couple different versions of the heat pumps, right? The one that everybody knows and loves and typically is using in New York City. We have over 40,000 of these installed in New York City. The VSHP is just your standard compressor in chassis. The compressor actually slides into the cabinet. For service purposes, we can keep 25 of these things, 30 of them down in the basement. When they break, instead of working in their apartment, we can bring that chassis down to somewhere to service it, fix the components, and then it's ready to go into the next apartment. So that's the nice thing about these from a service perspective. All the access is right through the front where you see that cardboard. That's where the chassis slides in and out, so you don't have to worry about a ceiling access panel. And I have some pictures later in the presentation with the access panel in front of the heat pump, and from a finished perspective, you just see sheetrock, you see an access panel, you open the door, and everything's right there. So the VSHP comes in two efficiencies, your standard efficiency and your high efficiency. Really, the difference in efficiency is the components, right? You use the different heat exchangers, so you exchange more heat, and you get better. And what we care about most today is the efficiency in heating season, because it's really the temperature of the water that changes in a conventional system versus a geothermal system. We're getting that colder water, so the units are going to operate at a much colder water temperature. So your COP, your performance, your efficiency in heating is worse in a geothermal system. The VSHY is the hybrid system. So we talked a little bit about hybrid systems where we're using a boiler of some sort that's going to inject heat into a hybrid loop because we can't get enough ground area for a geothermal 100%. This is different in the fact that a hybrid heat pump has a compressor for water-cooled cooling, but in heating mode, I'm actually going to get 100 and 105 degree water for the sole heating purpose. And so it's kind of a hybrid system. Compressors don't run in the heating mode. So that's a hybrid system. And you can use that in the geothermal application because you're still going to be rejecting heat to the ground during cooling mode, and in heating mode, you do need 100 and 105 degree water. 105 is kind of that magic temperature because you don't need to insulate above 105 degrees. So engineers are specifying 105 degree heating capacities. So you can get the 105 from a water-to-water heat pump. You can maybe use solar. We're doing a couple projects where we're using solar heat to raise the temperature of that water, and we can get heating at 105. You can also use that coil for a free cooling or heating coil, which a couple projects we're talking about that. And then you have the compressor for backup cooling and heating. Then we have the VSHP-E and YE, so your regular conventional heat pump and your hybrid with a built-in energy recovery ventilator. So the ERV is going to be, these units typically are installed in the exterior parts of the space, so along the walls, and they're exchanging heat from your bathroom exhaust. Bathroom exhaust has to go out, so in lieu of centralizing it up the middle of the building, we can free up shaft space, bring this bathroom exhaust through the heat pump, through the exterior wall, bring outside air through the heat exchanger on the other side, reclaim some of that heat from the bathroom. We can bring outside air up to 150 CFM pretty much 24/7, right? And we have special freeze protection sequences so we don't freeze coils, and we don't bring in cold drafts into the space. So here's a conventional heat pump loop. This is what we've been doing for 25 years until we realized geothermal in New York is a possibility. We have, here the graphic shows a closed circuit evaporative cooling tower. Could be an open cooling tower and a boiler, right? So this graphic is showing generally, as long as I'm seeing 70 degrees, somewhere between 60 and 90 year round, I can get simultaneous cooling and heating. Different than a 4-pipe fan coil system where I need to have two sets of pipes, one sending 45 degree water for cooling and one sending 160 degree water for heating. As long as I'm getting 60 to 90 in these two pipes, I can get cooling or heating any day of the week, any time of the year. The heating season, I'm usually running about 70, and in the cooling season, I'm running 85, 90 degrees. In a system, day like today, you have some people that want some cooling because there's a solar load on their windows, some people in heating, so I'm exchanging heat with cool in the same loop, which is what we talked about one of the other presentations on active thermal energy storage. So we're actually exchanging heat within the loop. Sounds like there's some tax credits on that, which I was anxious to hear about that this morning. So here we're exchanging some units in heating, some units in cooling. The ones that are in heating are lowering the temperature of the water. The ones that are in heating or cooling are raising the temperature of the water. So we're maintaining that 70 degrees. In cooling, you'll see it, entering water of 85, coming back at 100 degrees. The cooling tower rejects the heat. Heating mode, it's running out at 70, coming back at 55 degrees, 58 degrees. The boiler injects the heat. Geothermal, we don't have a boiler. We don't have a tower in the perfect world. In a full geothermal system, hybrids, you might have supplement systems to try to add heat and reject heat accordingly. But this is basically what we're talking about today. And again, from my perspective, from our heat pump's perspective, I don't really care where the water comes from. It's about how the unit operates based on the temperatures it sees. This is the hybrid loop. So in this case, you're going to have a slightly higher temperature loop for a hybrid system. This is what we were talking about earlier with a hydronic coil. I can get some heating on a day like today with 80-degree water. So we run 80, 90-degree supply return water temperatures, so it's a little bit higher water temperatures, which you can get in a geothermal system. So something to consider from a hybrid heat pump and potentially a hybrid geothermal loop. So this slide talks about, a lot of times we'll do these residential buildings with developers and they'll ask me, what is the contribution electrical utility-wise at the building level and at the tenant level? So they use it, one, to sell it to their realtor so they can sell it to the tenants that are moving into the spaces. Your utility bill is going to be higher or lower based on the system. In a conventional heat pump system, 80% of the utility and 100% of the system is at the building level. So that's your boilers and your towers and your pumps and your heat exchangers and your glycol feed and everything that goes into the utility side of maintaining that loop between 60 and 90 year-round. 20% at the heat pump level, so in the apartment. So 20% of the utility is running the compressor in the space in the apartment and the fan and the electrical components. Geothermal, a lot less on the building side, so I don't have the same size as cooling towers and boilers at the apartment level because in heating mode I have a lower condenser water temperature, it's less efficient. So it does actually add a little bit of utility at the tenant level. And then the hybrid system, all I'm doing from a utility perspective at the tenant level is I'm running a fan. Because I'm getting hot water, it's a fan coil. The building is working extra hard because I'm running boilers and I'm trying to get that temperature up. Kind of talked about that. This is basically what the heat pump looks like behind the wall. The casing in the back, which has the risers attached, you can actually get the risers from the factory. We can size the risers for you. That gets installed first during construction phase. Framing's going up, those are going on slab. The chassis gets slid in. All of these parts are accessible from the front. It's kind of the phases of the install. When you're putting track down, we're putting cabinets on. Cabinets do need to be installed after skin's on the building so it's not exposed to the elements. Chassis aren't going in until typically we're ready for cooling and heating. There's your access panel on your bottom right there, your stage 4. Where that access panel, we have a lot of different configurations, custom paint colors, so the architects in the room. We do have a flangeless option where you can't see any flange, and I think that picture actually is one without the flange. Very cool, it's just a reveal where the return air goes back to, and all components are accessible through that front access panel. Just some features and benefits about the product. It's the difference between a silver series and a gold series. These units aren't typically ducted. They are built 10 feet tall, so I can put these units all the way up to the ceiling. I can free blow into the room in multiple discharges, or I can duct them. The problem when you duct them is some of those vibrations that may be in the unit are going to get into the space. Right? They're going to get through the sheetrock, they're going to get through all the ductwork, so we want to isolate any ductwork from the heat pump, so this integral flex, that yellow piece you see there, we can do that at the factory. That's called our Gold Series. More standard features. This talks about our sound package. When we made that move to heat pumps in apartments, the first thing we had issue was everybody's heat pump was too damn noisy. Too noisy, you got a compressor in the space. I put a 2-ton condensing unit in my backyard. Now they want to put it next to your bed and it's supposed to be quiet, right? You're supposed to sleep with that. So all the manufacturers had to kind of reinvent the wheel from that perspective, say, how do I make this unit quiet? Omega happens to be the quietest in the industry. I'll say that hands down. I've sold a few different manufacturers. They do a lot of these really cool features and benefits that I can't get into today, but definitely take my card afterwards. If you have any questions, let me know. Through the controller, we can see a lot of the temperatures, refrigerant temperatures, water temperatures, air temperatures, especially in a geothermal loop when we're talking about thermal balancing. Knowing what those temperatures are at the water side is very important. Techs can go actually dial in and see what those water temperatures are. Here's your ERV, which we touched on earlier. We can get 80% sensible efficiencies, which do meet the passive house requirements for heat exchange from the outside air through the toilet exhaust. These are pictures of access. And here's the efficiencies that when the utilities are looking at it, reviewing to see if it qualifies, we can, with a ground loop on our high efficiency, see anywhere between 15.4 and 19.7 ERs and 3.4 to 3.8 COPs. Highest in efficiency in the market. And finally, we test everything in-house. It's a third-party certified testing facility that we do all of our psychrometric testing. Any engineer that wants to see something special, we can do it for their job. So if we're experimenting with really low water temperatures or really high water temperatures, we can do it in our factory. If you have any other questions, come find me after the show. And that's it for now. Thanks.
Is this going to work, or should I use the, okay. All right, everybody. So I'm here to talk to you all today about balance. So Brian had touched on it a bit in our initial discussion of these kinds of systems, particularly in high-rise buildings. One of the main things that we contend with is trying to find an adequate balance between our heating and cooling loads. So a tall building, as we all know, warm air rises. They have a whole lot of surface area, sucks up a lot of sunlight. You'll tend to see a much higher cooling load in a tall building than you will a short building in a similar climate. On top of that natural tendency for these tall buildings to have a lot of cooling load, a lot of times, as we try to create more efficient buildings, a lot of these levers that we have to pull will have an outsized impact on our heating load as compared to our cooling load. You make your building tighter, you have a more efficient ventilation system, you reduce your domestic hot water usage. All of these will knock down your heating load. It'll knock down your cooling load as well, but probably not to the same degree. So I have a little diagram up here that shows, this is a sample one of our projects. You can see that the lighter color is what you would have with a minimum code compliant building. And then in the darker color is after we've gone through and done all of our energy efficiency measures. You'll notice at first we have about twice as much total annual heating as we have in our cooling. And then when we're done with that, our difference is only about 40%. So, as we say, our concern is with cooling dominance. You still have 40% more heating. What's the problem? Innate to a heat pump, you have to contend with heat of compression. So for a heat pump, you have to put energy in to move energy around. If you are heating, that energy that you put in is contributing to heating your space. If you're in cooling, that energy you put in, you also have to get rid of. So when we look at what's actually finally making it to the ground in a geothermal system, you have a gain, so you won't have to pull as much heat out of the ground in heating because you have that additional, and then in cooling, the reverse. So that's how we get from a building where we said before we had about 40% more heating than cooling. Once you factor in this heat of compression, in this particular example, now you actually have 10% more total cooling over the course of your year than you have heating. Why does this matter at all? So, as we all know, our ground is a thermal reservoir. If every single year you are dumping in more heat to the ground than you're taking out, you're going to slowly see the temperature of the water that you're pulling out of the ground rise year over year. This is going to reduce your cooling efficiency. It'll help your heating efficiency a bit, but it will reduce your cooling efficiency. And if you allow this to run on over 50 years of operation of a building, eventually you're going to lock out your compressors. Your system is not going to work at all. So to counter this effect, we have to find some way to get rid of this excess heat year over year. We'll go through a couple options. We have some levers we can pull to take care of that. First and foremost, we can take care of this through changing the geometry of our bore fields. If you're able to spread out your boreholes or drill them deeper, you're essentially increasing the surface area that you have to let heat escape from that system. Now, a lot of times in New York, particularly in these small footprint, high-rise buildings, we're pretty limited in what we can do to this, in this regard. Being able to drill deeper than 500 feet helps, but in general, we're constrained on a small site. We do this as much as we possibly can, and then may have to use other alternatives. So just a quick case study example. So this is, stretching the definition of a high-rise building a little bit, but this is an affordable housing complex in Austining, New York. It's currently in design. So as we're going through the design of this building, we develop our building energy model, we get the loads, we find that does a bit more heating than cooling. So when we first plug in, we're maxing out our boreholes all tight together. We get 56 of them on our site, and we see an increase in our temperature year over year. Eventually we get outside of our bounds over 20 years. So we run another iteration. We actually reduce the number of boreholes. We spread them out a little further. We go from 20 foot on center to 30 foot on center. We drill them 50 feet deeper, and we see a flatter curve We don't see that runaway increase in temperature, and it's a more sustainable system. Now, as we said, a lot of times you're limited by space constraints or drilling depth constraints, or potentially you don't have, it may cost more to drill deeper or further. So another type of system that we look at, we call it a hybrid system. So what you'll do is you'll size your bore field, you'll meet the heating load, or as much of it as you possibly can, and then whatever you cannot meet with that heating load, you will meet with some other, cooling load, you'll meet with some other thermal resource. So in this case, we're calling it peak operation. So what you'll have is as your condenser water temperatures rise, and your geothermal system is not able to keep up, you will have some type of chiller or other thermal resource will come online and knock those temperatures back down. And that will serve to balance your system over the course of the year, and it's fairly simple to install. For an example of that, some of you may have seen this building on our tours on Monday, 25 Stewart Hotel in Bushwick. Again, significantly higher cooling loads than heating loads. And we have the very eloquently named rat tail on the corner of this building where our boreholes are drilled. We don't have any space to expand that bore field. We're very limited. We're stuck in our little spot. So in order to keep the balance in the system, we have a system of 8 air source reversible chillers that come online to meet any cooling loads that our geothermal system is not able to keep up with. And our third and final option that I'll discuss, so you can take this hybrid system and not run it as a peak to meet your peaks. So we would then schedule, instead of where on our hottest days of the year as our condenser water temperatures are rising, we actually balance our system in the colder months of the year when it's more efficient to run a dry cooler or some other thermal resource to be able to reject this heat. It requires a fairly sophisticated BMS system, so you need to track over the course of the year how many more BTUs are going into the ground than coming out. And then you will design your system to be controlled to run for enough hours and reject enough heat throughout the entire course of the year to make up that difference. So for an example of a project where we had this installed, again, another one on one of our site visits, 1515 Surf in Coney Island. So we, for this project, installed a dry cooler on the roof, and we have our BMS system with all of our BTU monitoring, and we will track the total number of BTUs that go into the ground, the total number that come out, and we have a system that will run and totalize the hours and totalize the BTUs over the course of the year. So in a number of years, as our condenser water temperatures rise, this system will kick on, and that will stop our annual thermal drift. So just kind of in summary, comparing all of our 3 options, your experience is going to vary with all of these. This is a very general rule, and different solutions work for different clients. So obviously, the first one, capital cost. Drilling a borehole is really expensive. If you find that in order, to keep your thermal drift under control, you're going to need to drill a lot more boreholes, you may have a situation where it's going to be cheaper up front to install one of these chillers, install one of these dry coolers, or some type of hybrid system to keep your system in check. The flip side of that is, well, in addition to capital cost, you have to consider your operational costs. It costs money to run one of these dry coolers or chillers. It does not cost that much money to have a borehole in the ground. Generally, when we look at this hybrid system run in the winter and we're running a dry cooler, it's more efficient. You probably don't have to have a compressor like you would with a chiller. You're just rejecting it straight into the cold air. You're going to use less electricity that way. Generally be a cheaper system to run. Factoring into capital cost, schedule impact. If you have to drill more boreholes further out, that takes time. We don't have limitless time. Time is money. So this is another scenario where you may want to use one of these 2 types of hybrid systems to compensate. Controls complexity. It's not complicated at all to run a bore field with a couple more boreholes or further apart. However, once you start adding these separate hybrid systems in, depending on the type of BMS system the customer has, you somehow need to integrate that and that's something that you need to work with in the design phase, and that factors into your decision making. I will say a dry cooler tends to be much more complex to control and install because you have to be aware of what your outside temperatures are versus your loop temperatures. You obviously cannot cool your loop and cool your system if it's warmer outside than your condenser water is. There are in impact, so with rebates in the IRA, you are able to claim depreciation on what are called energy properties, anything that exchanges heat with the ground. So if you have a chiller, a cooling tower, or a dry cooler, it does not count towards that. So it's something to look at as you make your decisions. And finally, all of this stuff takes up space. So as we talked about, roof space is very valuable. To put a dry cooler on the roof, to put a chiller on the roof. They're noisy. We've had some instances where, we want to put this up, we want to run it for a long time, but they're saying, hey, we have a pool on our roof. People using the pool don't want to listen to our dry cooler running. So it's another just a factor you have to keep in mind as you're making this decision between any of these three options. And as we said before, of course, the footprint in the ground, enormously important, particularly in these tight, high-rise buildings and the places you would be installing them. Okay, and that's all I have. Thank you all.
Could we get one more round of applause for Sam, Jason, and Brian? At this point, we can open up to questions. John Rath has a floating mic, and he will find you.
You call on the person so I don't get...
Hands, please.
Okay, I have two questions for Jason. You were talking about the vertical stack units in the apartments, and you have an option with an ERV. So two questions about that. One is, you talk about 80% sensible, but you didn't talk about the efficiency for latent. And the other part of that is, how often do you have to change out components with the ERV as compared to, say, a compressor?
So from the efficiency perspective, typically the passive house requirement is a sensible requirement. So that's why we specifically talked about that. But there is a latent component to it, though. The fact that it is a energy core, you do get a latent benefit from it. But the reason we mentioned the sensible is that 80% is a number for the passive house requirement. So that's why we specifically brought that up. From a service perspective, really, it's a cleaning process, right? It's an energy recovery core. There are a couple fans in there that do need to be potentially replaced at some point, but there's no bearings, there's no belts that need to be greased for that matter. So really, the access is from a cleaning perspective. You have to clean the core, similar to cleaning a filter, right? And the compressor, I would say you're going to lose a compressor long before you're going to lose one of these small incremental horsepower fans for the RV. So you don't need access to very much. But the good news is with this product, the access is still all through the front. You have a larger access panel, and it's all from the front, single point access for that ERV. Eugene, do we have a latent efficiency on that core by any chance? Eugene is with the manufacturer, by the way. He's sitting over in table 7. Do we have a latent number for that?
There's latent, depends on the condition. So the 80% sensible is the heating requirement, as mentioned. The latent will vary anywhere from 60 to 75%.
60 to 75% latent. Okay. That's based on design conditions?
It's based on design conditions.
So ideally that, hot, humid day, latent transfer. Thanks.
Okay, my name is Charles. Question is for Sam. I was looking at those charts, and I haven't seen domestic hot water production in the chart, which could definitely shave off the peak in cooling. And I wonder if you have done calculations and simulations on using that as a way of getting rid of that peak, and that will be year-round, which will increase your heating load, obviously.
So absolutely, and on a lot of our high-rise projects, we do have, domestic hot water heat pumps. We tie that load in. It was probably very small up on the screen, but those loads shown actually did include domestic hot water.
Okay.
So yes, absolutely include that. You know, try to find a beneficial use for that extra heat, and domestic hot water is usually the first place we look.
All right, thank you.
John?
Hi there, my name is Chase from Ramble. My question is likely more New York City specific. I know there's a lot of high-rise buildings whose underground footprint is taken up by large subway stations. I'm wondering if any of you have any experience with any waste heat recovery or subway heat recovery for that matter.
Subway heat recovery?
Yeah, I don't have any experience with subway waste recovery. I know that that's been talked about. I don't know that anybody's actually done that in New York yet. You know, obviously they're pumping millions of gallons of water out of the subway systems every day. Great opportunity. I don't know that it's been done. As far as sewage heat recovery, most of the projects in New York that I've been involved with are at the building level before it exits the property, not anything from a municipal, you know, line in the street. So, you know, obviously the capacity is limited based on that. A couple of projects we've been involved with, you know, you're talking about 300-400 units, and you're still barely an average daily peak or an hourly peak of around like 100 gallons a minute outflow. So that's like your average during the day. Obviously it goes down at night, and that's about minimum the flow that you would need for some type of sewage heat recovery system to try to get any benefit, which then would require a pretty large storage tank of effluent, and most developers don't really like to have 50,000 gallons of stored effluent on the property. So those are some of the challenges you have to think about. There's also products out there that take the heat from the effluent directly right back to the domestic water, so maybe that would be a better use for that you can get by with smaller flow rates and smaller tanks. But if you're using it as a passive system and trying to do heating and cooling and supplement the geothermal system, generally requires a large holding tank, because you're doing multiple pass. It's not a single pass through in order to get the most benefit. So again, but there's a lot of regulatory stuff around that you have to work through. And then, you know, just looking at, you know, your wastewater flow rates and try to analyze that, see what kind of capacity is available.
Yeah, can you talk a little bit about the pressures that are in the condenser water loop line, you know, for these really tall buildings, you know, what you do to limit the pressure?
Yeah, I mean, obviously, when you start to get around, you know, 30 stories or so, you're gonna have to start putting pressure brakes in. So if you had a 60-story building, you've got 2 pressure brakes in just the condenser loop, but the other pressure brake with geothermal that you really have to look at is that pressure brake at the bottom before you exit the building to your lateral header piping for the geothermal system. That's actually gonna be your weakest point in that entire, like if you had no heat exchangers, the weakest point in that whole system where you're gonna have the greatest amount of pressure is in the lateral piping. You would think it'd be in the vertical bore, but that's not the case, because generally you have grout and external pressures of hydraulic water, et cetera, in the borehole that's pushing back on the pipe. So the worst case is that lateral piping. So you for sure have to put a pressure brake or heat exchanger basically at the ground level before you exit down to your lateral piping to protect that. So yeah, I mean, and then you think about that. So, you know, every time you go through a heat exchanger, you're losing a little bit of temperature, right? You're not designing for a 0-degree approach. So you might have a 2 or a 3-degree approach. So if I've designed my ground loop at 90 degrees and I've got 3 pressure brakes, my top level heat pumps, my top 30 floors are probably gonna be at 100 degrees. So those are all implications just because of the pressure that now impacts the efficiency of the system. So those are all considerations.
And I will say as well, that's a big consideration we have when we're talking about dry coolers, which do generally need to go on the roof. We'll decouple those as well, you know. So for a pressure brake, as we say, you know, a roof, you have a tremendous amount of fluid on top, and we don't want that pressure on our geothermal manifolds and things like that. But additionally, we decouple because if you're going to have a dry cooler exposed to colder air than anywhere else on the system, we generally will have a higher glycol concentration in that particular loop as well. So an added benefit, you know, we decouple for pressure and for glycol concentration.
Okay, Colin, you want to?
Any further questions? We're a couple minutes from lunch. I'm sure everybody's excited about that.
Speaking of lunch, I think we owe Jason, if I'm not mistaken, a thank you for providing lunch for us today. And then a reminder, anybody that's looking for continuing education units, on the back table I've got pages. I need your signature and your printed name before you leave. So how about another final round of applause for Colin and his panel? And I'd catch the folks before they get out of here if you have additional questions.